So before talking about the threads, if you have to understand why threads are so useful mechanism, you should actually understand why we cannot do certain things in an efficient manner without using threads. Okay, I don't want to confuse you, just try to understand this. See, I'm going to explain you threads in the next video, but if you have to understand why threads are required, you should understand what happens or what are the disadvantages if you are not going to use the threads. So for that reason, even though we don't have this particular system call in the syllabus, I want to discuss about these two system calls. Okay, so actually nothing is mentioned in the syllabus about this fork and execute system calls, but then I think once or twice I have seen some question about it. Probably earlier maybe that was in the syllabus, but currently it is not there in the syllabus, so you need not by heart it for the exam. But if you can understand this, I can make the threads concept simple. Otherwise you will not be able to appreciate why threads are required. Okay, so let's talk about this system call. Two system calls, fork and execute. Okay, execve, these are the two system calls, and these two system calls are available in many versions of many flavors of Unix and also in Linux. And those who have already worked on Unix and Linux, it will be easy to understand, and anyway for others I'll try to explain. So the main advantage of using a fork is like this. If any program, any process, if it is executing and if it suddenly calls the fork system call, let us say this is a process, and if it suddenly calls the fork system call, suddenly it will create a new process. This will be called as a parent, the one which has executed the fork system call, and this will be called as a child process, right? Parent process and child process. Now what is the advantage of having parent process and child process? So let's say, in order to explain it clearly, okay, let's see what is happening here. Assume that this is the main memory. Okay, and somewhere here there is a process P1. Let's call it as process P1. Process P1 is executing, and what will be associated with a process? Instructions will be there. Let's call this section as instructions, right? Or .exe code, which means executable code, .exe. Okay, and what will be the other parts? Static variables or global variables will be there. And what will be the remaining things? We'll have one is stack and other is heap, right? As the process is executing, it will be using many variables, and it will be executing some instruction, right? At the end, program counter will say what instruction it is executing, and this is the image of the process in the memory. And whenever it executes fork system call, let us say one of the instruction in the execution sequence is a fork system call. Whenever it calls the system call fork, then automatically we'll get into the operating system function, right, which is fork, and this particular function, it will create a new process, let's call it as P2, right? And this new process is going to be a child of this one, and this entire thing will be copied here, right? So what will be copied? The entire memory image completely, whatever is in the stack, whatever is in the heap, whatever are in the static or global variables, and whatever is in the instructions, completely everything will be copied here. A Xerox copy of this will come here, right? Now why is it useful? You can think of it this way. Let us say there is a process which is a server, okay, a server, and let us say it is a web server, okay. And what is its main purpose? Whenever any client approaches this web server, it is supposed to send the web pages, okay. So if it can handle only one client, isn't it? So whenever someone approaches it, it can send the HTML, and while it is sending the HTML files, if some other client approaches it, then what should it do is it can create an image of the same thing using fork, right? And the good thing about the fork is, if you are having fork written somewhere, let us say fork is written somewhere, once this instruction is executed, we are going to create two process, and both the process will execute from the next line. Now this one can handle this client, and the new client request whichever it got, that will be redirected to this, and this one can perform the provide the service to the client. This is how you can solve the problem of handling many requests at the same time, right? But then there is a problem with this. The problem with this particular approach is simple. The problem with this particular approach, if you can see, is you have to call the operating system, and now operating system has to create you an identical copy, isn't it? And then both of them will be executing parallelly, right? So now this is a process and this is another process, and both of them can execute parallelly and provide the same service to different clients. Got it? So how can they provide same service to different clients? I'll get back to you. So how to identify which one is child and which one is the parent? I'll tell you that. But try to understand one thing. Now creating a new process using the fork system call will actually require a context switch, and you have to change from user mode to system mode, isn't it? Initially you are executing in the user mode, now you have to go to system mode and execute a different code. Then because of this context switch, there has to be a lot of instructions which have to save the context, and these instructions have to be executed, which is a overhead, isn't it? Yes, you are getting two processes, but what is the penalty you are paying? There is an overhead here, clearly, right? So that is why creating two processes to provide us some service is actually a overhead, or we have to go through some penalty. So this is why we are not going to use it. Got it? So that is why we need a mechanism called as threads. That is the reason why we need threads. Now let's come back to the fork system call again and see what are the other ways fork is being used. Now whenever you call fork, generally fork instruction will be called like this. In a program or a process, the fork system call will be called like this, something like this: int I equal to fork. Okay. Now by executing this line, fork is going to return some value into I, right? So after this you are going to write like this: if I equal to 0, then you are going to write something here, and if I is not equal to 0, we are going to write something here. This is how generally the structure of a program which is using fork look like. Now I told you that fork is going to create two processes, one is parent and other is child. Actually it will create only one more process. Already one process is existing, one more process will be created. Now since both of them are identical twins, they should know who is parent and who is child. That is why the fork returns. So fork is going to return I equal to 0, fork is going to return a value 0 for the child process. Therefore if I put I equal to 0, the process which will execute this code will be child process, right? And the process which will execute this code will be parent process, right? See, in case if you are not understanding it, don't worry about it. This question will not be asked in GATE, but if you can understand this, it will make my threads topic easy. That's it. Even if you don't understand it also, you can listen to threads, that is fine, but it is interesting. Just see how it is being done. Okay, so now see this. So what is being done here? I have called the fork, and fork has created a new process. Now how can I distinguish which is parent and which is child? Because fork is going to return a value of 0 to the child process, and is going to return a value of non-zero, right, to the parent. So what parent is going to get is process ID of child will be returned to the parent, and the child will be getting 0, right. Now whatever code you execute here, you write here, it will be executed by the child process, and whatever code you write here, it will be executed by the parent process. Generally what people will do is, here they will write the code in such a way that this entire body of the child will be replaced by some other program, and we will start executing that program, right. So for that purpose we are going to use one more system call, which is called as execve. This is the system call. If you are going to call this system call with a program with some binary file, then this entire image is going to be replaced. Actually a new program will be loaded into this area, and that new program will start executing, which means initially when child is created, that child will get the copy of the parent. But if you don't want the same thing to be done again, just like in case of this, if your program is not like a web server, then if you want to execute something else, then you can completely replace this process with some other thing, and then you can start executing it. Got it? So in general, how people will make use of this system is, if you want to perform if you want to execute something, then a process, a parent will create a child, and this child code will be replaced by that particular program. And once this child is execution is over, it will write exit at the end. It will write exit, which means the child is over, and it will write exit, and it will return to the parent, right. Now what parent will do is, till the child process is executing, in general it will try to wait for it. So it will try to wait on I. So where I is the process ID of the child. So this is in general what happens, how people make use of it. You need not see, it is not a compulsion that always when you create a child you have to run a different program, but in general most people use it for that things. For example, those who have used this Unix, those who have attended this Unix course in your college, you must be aware of this concept called as shell. C shell, Bourne shell, Korn shell, all these are shells developed by various people, right? So what is the main importance of the shell? When you start executing a shell, when you start running it, you are going to see a command prompt, isn't it? And when you type something on the command prompt, then that particular instruction is getting executed. For example, you might try to write cat, right? Or you might try to use the instruction ls, right, list all the files in the directory -l, something like this. Now these are the commands which you are going to give to the shell, right? First you will start executing the shell, and then you are going to type something in the command prompt, and that particular instruction will be executed. What is the concept behind it? Simple. So initially your shell will be running as a process, and whenever you give a new command at the shell, our shell internally will call the function, the system call fork, which will create a new process, and that will actually be containing the same thing as the shell, but then it will use the execute instruction in the child code by like this here, right? It will use the execute instruction in the child code, and then it will execute this one, right? And parent will wait for child, and child will actually execute this binary code ls -l, and the binary code for this ls has to be present in the default directory where you can go and search it. Got it? And after everything is done by the child will exit, which means it will display all the results and it will exit, and then your parent will continue. Got it? So okay, whatever I told you, I just wanted to give you a brief overview. Actually, talking about Unix and Linux, is actually a course in itself. Like, it is a very big course, just like operating systems, but we don't have that course in the syllabus. Maybe I'll do it as a separate course later if possible, but I'm not going to promise you anything. Later, if I have time, I'll do that. But for now, you try to understand all this. Everything I discussed here is to make one point clear. If you want to perform parallel execution of the same thing, using the fork and execute, or using the fork call, is actually not very useful. The reason is, yes, it is useful, but it is going to have incur some penalty. What is it? Whenever you want to create a new process, you are supposed to execute the fork system call, and that involves context switching as well as change from the user mode to system mode. And whenever we go into that system mode or super user mode, then it is obviously going to be costly, right? So we need an alternative in which we don't actually change the mode from user mode to system mode, right? But then we want our work done efficiently. So that is where threads are going to be very useful. Okay, in the next video we are going to discuss about the threads. Okay, fine.